All right, so part B for this problem, with a long thin rod carrying a charge density lambda and lies along the x-axis moving in the x direction with a speed of capital V. We want to find the magnetic field at point P. Okay, using Biot-Savart's law, we could find that the magnetic field caused by a long thin wire at point P is going to be mu naught times the current over 2 pi r, where r is the distance between the closest point on the wire to our point P. Okay? The only variable we don't know here is our I. So how can we find our I? Well, our current I is going to be equal to our charge density times the velocity V. Okay, and this is because if we look at our units, we'll see our charge density is charge per meter, and our units for velocity is meters per second. Our meters will cancel and we'll have charge per second, which is what we wanted for our current. So replacing that in our equation, we'll have mu naught times lambda V all over 2 pi r. Plugging this in, we'll have mu naught is equal to 1.256 times 10 to the negative 6 times lambda, which is 32 times 10 to the negative 9 coulombs per meter, times our velocity, which is going to be 2.1 times 10 to the 7th all over 2 pi r, where r is going to be our 18 centimeters, or 0.18 meters. And then that's going to give us 7.466 times 10 to the negative 7 Tesla. And also, one thing to add, we will see that our direction of the magnetic field will be in the positive z direction, because if we look, if our velocity is coming this way and our magnetic field wraps around, it'll come out of the page at point P. And that is it. Alright, so for part C of this problem, we're going to find the force exerted on an electron moving with velocity 1.1 times 10 to the 7th I hat meters per second. Quite fast, huh? At point P. Okay? If we know our forces, so our net force on our electron is going to equal the force caused by the electric field plus the force of our magnetic field, then we must calculate each individual force. Simply put, our force caused by the electric field is just going to be equal to our charge Q by our previously calculated electric field E. Okay, and if we plug that in, we should get a value of 5.114 times 10 to the negative 16 newtons in the j hat direction, because it's pointing in the positive y axis. And then if we want to calculate the magnetic force, we'll have FB is equal to Q times V cross B. Okay? And we're going to have to use a little bit of right-hand rule here. We know that the magnetic field is coming in the positive z direction, because we are going to the right and coming out of the page. Therefore, our velocity is going to the right. We use our thumb pointed in the direction of the velocity, take our four fingers, put in the direction of the magnetic field, which is coming out of the page. Thus, our force should be coming downwards. But because we have a negative charge, it's going to be flipped upwards. Okay? So we have that given, and we have our charge times the velocity. Writing this out, we have Q, which is 1.6 times 10 to the negative 19, times V cross B times sine of 90, where sine of 90 is just 1, as our velocity 1.1 times 10 to the 7, times our magnetic field, which is going to be solved from the previous problem as 7.466 0.466 times 10 to the negative 7 Tesla, okay? And then that'll be evaluated at 1.315 times 10 to the negative 18 newtons. Okay? And also because we have a negative charge here, this force caused by the electric field is going to be negative. Therefore, it's going to be attracted to our wire. Okay? We see that our magnetic force is going to be pushing the electron away, and then our electric force is going to be pulling our electron towards. Therefore, we're going to sum the two to have 1.315 times 10 to the negative 18 newtons minus 5.114 times 10 to the negative 16 newtons. Thus our net force is going to be evaluated as negative 5.10, because it's just two decimal places off from our other one. 5.10 times 10 to the negative 16 newtons. And that is our final answer. And one touch is going to be in the negative j hat direction, which means our net force will be coming towards the wire of our electron.